Okay, let's talk about carboxylic acids and carboxylic acid derivatives. Carboxylic acids are really common in everyday life. Citric acid, often used in baking, is this structure here, and it's from citrus vegetables. There's carboxylic acids like oxalic acid in green leafy vegetables. There's carboxylic acids in vinegars and in many pharmaceuticals, including aspirin, one of the oldest pharmaceuticals of synthetic origin. So just looking at that in more detail, so we talked about aspirin. The simplest carboxylic acid is formic acid. And formic acid is what those nasty ants will put into you when you get an ant bite. Lactic acid, that's what builds up in your muscles when you have exercised for a prolonged period. And many other acids shown here. Ibuprofen, common anti-pain medication. There are versatile intermediates in organic chemistry, so we can turn carboxylic acids into reactive intermediates like acid chlorides. We can make them into amides, we can make them into esters, and we can make them into acid anhydrides, amongst other things. Okay, so when we look at the structure of carboxylic acids, it's important to look at the components of that functional group. So there's a carbonyl group, the CO double bond here, and then there's the hydroxyl group, the OH group here. Now, although it has those two components, really carboxylic acids are their own distinct functional group. They're quite different to other carbonyl compounds, such as ketones and aldehydes, and they're quite different to alcohols, which also have OH groups. And one of the most important differences is that they're weak acids. So the Ka, the dissociation constant for acetic acid, is 1.8 by 10 to the minus 5. So it's weakly dissociated in aqueous solution. They've also got much higher melting points and boiling points than the corresponding alkanes and other related compounds like aldehydes and ketones. And that's largely because they form really strong hydrogen bonds with each other. So we have this dimeric hydrogen bonding arrangement that makes these molecules sort of stick together. To name a carboxylic acid, we just replace the E at the end of the parent alkane with oic acid. So butane would become butanoic acid, and so on. And there's a hierarchy in terms of naming, and carboxylic acids sit right at the very top. So most other things, or pretty much everything else, will be named as a substituent on a molecule that's then named as a carboxylic acid. So this molecule here is 3-hydroxy-4-methoxy butanoic acid. This compound here is 2-hydroxy benzoic acid, and so on. Looking at their names, well, there's the IUPAC name, but then there's many of these molecules have been known for a very long time, and so they have common names that they're commonly referred to. It's interesting to look at the derivation of these names because they're common from nature. Many of the common names of carboxylic acids are related to where they were originally found. So formic acid comes from the Latin for ant, which is formica. Acetic acid from the Latin for vinegar, acetum, and so on. Interesting one here is the 4-carbon carboxylic acid, which is butyric acid, comes from the Latin for butter, and butyric acid is one of those volatile components of butter that gives it its distinctive smell. To make carboxylic acids, a very common way to do that is to oxidize a primary alcohol, and you can use chromium-6 reagents. Even though they're carcinogenic and quite toxic, they're also very effective at doing these types of oxidations. Or you can also use other oxidants such as potassium permanganate. From carboxylic acids, we can talk about derivatives. So there's acid chlorides, which are quite reactive, acid anhydrides, which are also reasonably reactive, esters, where we have a CO bond attached to the carbonyl group, and amides, where we have a CN bond attached to that carbon. Now, each of these are named as carboxylic acid derivatives because they can be formed from a parent carboxylic acid. And so it'd be common to make these molecules from a carboxylic acid synthetically in an organic lab. Here's an example of a carboxylic acid derivative from nature. This is cantharidin, which is a really powerful vesicant or blistering agent that's produced by certain beetles, the blister beetles. And if you get that on your skin, it will cause very profound blisters. So let's look at the first derivative, esters. We formed them from carboxylic acids and alcohols. So the simplest way to do this is to take a carboxylic acid and an alcohol and to mix them with an acid. It's a reversible process, but if we remove the side product, which is water, which is on this side of the reaction, if we remove that, then we can drive the equilibrium across to the ester. And esters are also commonly found in nature, particularly in fruits. And so many small volatile esters have familiar smells, such as allyl hexanoate, smelling a bit like pineapples, and other common esters like these ones here, isobutylformate from raspberries, ethyl butanoate from pineapples, ethyl isovalerate from apples, and isopentyl acetate from bananas. That's a very common one that sometimes is made in undergraduate labs as an experiment. There's other more, I guess, adult flavors and smells you can get from esters. So rum is quite often characterized by isobutyl propionate as one of the volatile components. Cognac normally has isopentyl butanoate as one of the components. And there's a very distinctive aroma in whiskies from this cyclic ester. So we call cyclic esters lactones. And this lactone is so specific or so prevalent in whiskies that it's actually got the common name whiskey lactone. So it's 4-hydroxy-3-methyl octanoic acid lactone. So to name an ester, according to our UPAC nomenclature, we need to go via a certain process. So we name it as a derivative of the carboxylic acid from which it is derived, and with part of the name coming from the alkyl or aryl group that's attached to the oxygen that's then attached to the carbonyl group. Okay, so let's go through it as a process first. So firstly, we look for the alkyl group that's attached to the ester. So the ester oxygen. So this is an ethyl group, so that's going to be the first part of our name. And then we look for the carboxylic acid from which this is derived. So this would be that part there. So that carboxylic acid is just the 2-carbon carboxylic acid, acetic acid. So that is going to be acetic acid. And we combine those two by putting the alkyl name first. So it's going to be ethyl. And then it's not going to be acetic, it's going to be acetate. It's going to be ethyl acetate as the name. And we can do that for any ester. Just name it in 2 parts and then combine them together. So we end up with ethyl from this part here, acetic from this part here. We change that acetic to acetate and we get ethyl acetate. And finally, one of the most common and important derivatives of carboxylic acids is amides. Amides are really important in biology. They're really stable towards hydrolysis. They can be hydrolyzed, but the conditions need to be very forcing. So you need to have reflux in concentrated acid or concentrated base, like sodium hydroxide or potassium hydroxide. However, biological systems find it really important to build and to degrade amide bonds. And so they've developed enzymes that can do these hydrolysis reactions even at room temperature or at physiological temperatures, such as 37 degrees. So for example, dimethylformamide is a common laboratory solvent. But if we treat it with water and hydrochloric acid and we heat it, then we can break it apart into its component parts, which are formic acid and the amine derived from this part of the molecule. Because we're doing it with the acidic conditions, the amine is basic, so it gets protonated, and we make the ammonium salt. Benzamide, this compound here, if we treat it with water and a base, we're going to hydrolyze it across here to give benzoic acid, but then that's in the presence of a strong base, so the benzoic acid will be deprotonated to give the benzoate, and the other byproduct will be this amine, which is actually just ammonia in this case. And obviously one of the most common places that we come across amides are in proteins, and obviously proteins are important for your diet from both meat and from vegetable sources. Amides are also present in bioactive molecules of all sorts of other types, including pharmaceuticals. But one of the more interesting ones that you will have probably come across is the compound from capsicums or from chili peppers. So chilies produce a molecule called capsaicin and a few related molecules that have an effect on pain receptors and actually lead to that hot sensation that you get from eating hot chili peppers. Amides are also really important in the polymer industry. One of the very earliest polymers was nylon, and nylon is just made from a diamine reacting with a dicarboxylic acid, or more often a dicarboxylic acid derivative like a diacid chloride or similar, and you end up making a molecule that has these diamine groups attached to dicarboxylic acid groups, so you have a diamide, a repeating pattern along the chain. And depending on the lengths of these chains, we can make different nylons. So the most common is nylon 6,6. We have 6 carbons in the diamine and 6 carbons in the dicarboxylic acid. Okay, so hopefully that gave you some background into carboxylic acid and carboxylic acid derivatives, their structures, their functions, and some of their reactions. Thanks for watching.